that'll change. All right, so let's say that we have a capacitor hooked to a battery, and here's a switch. All right. So capacitance, resistance, voltage. So this is an RC circuit, what we call a resistive capacitive circuit. All right, so RC circuit. Not to be confused with the drink called RC, which must be consumed with a moon pie. Some of you don't know what moon pies are. All right. They used to be good. I think they kind of stink now. Anyways, so switch open, nothing happens. Switch closed, all sorts of things happen. All right. Charge builds up on the capacitor. Current flows through the resistor. The delta V here will be a negative electromotive force things. We got all these things going on in the loop. Now the Kirchhoff or Kirchhoff law would tell us this, that the voltage source minus the voltage drop across the resistor minus the voltage drop across the capacitor has to equal 0, and we can write the voltage drop across the resistor as the time-dependent function of current and resistance, or IR, V equals IR, Ohm's law. The voltage drop across the capacitor could be understood as the charge function per unit time over capacitance. That's applying basically the definition of a capacitor. And that has to equal 0. So we're just applying Kirchhoff's laws, stuff we've learned, Ohm's law, the definition of capacitors, all this stuff had to follow. Okay. I wanted to start with this on Monday, but I wasn't here Monday, and then I forgot to start with it today. So here we go, separate lecture. All right. And so we have these things here, but you should know that this time-dependent function for current is the same as the time derivative of the charge function per unit time. Does that make sense? Isn't current just charge? How many charges are going past a spot every second? So the charge function, the derivative of that would be what IT is equal to. All right. So this means that our we can rewrite all of this, okay, as R dQt dt plus Qt per C equals that voltage, that EMF that's applied by the battery. So this up here is a differential of the charge time function. Okay? So now everything on the left-hand side is a charge, a function of charge in time. Okay, so we're getting, and capacitors, what are capacitors about? They're about holding charge. And what they hold charge is dependent on time, among other things. All right? So we're getting to something here. So this voltage so this differential equation that has some more work to be done on it is a statement that describes this whole circuit. So many of you are already in or past diff EQ. You've learned a lot of techniques. You'll probably take partial diff EQ, more of that when you get to university. And, you know, there's a lot. Differential equations, you know, they can describe anything. And there's a lot of differential equation types, ordinary, differential, partial, et cetera, et cetera. All right, so they are a very powerful tool, power series, et cetera, et cetera. So let's kind of, I'm going to simplify the notation a little bit just for this ease of not having to mess with everything. So one thing I can do, and I'm just going to do a dq dt, okay, so that I can rearrange this. So dq dt, so this part here, would be equal to v over r minus q over rc. Okay, so I'm just trust that rearrangement, oh, I'm missing an R up here. Sorry about that. Make sure you get that R in there. I didn't have that initially in the blue. And so we want to get a dq, well, we want to dq, we want to get the other differential to the other side, right? A differential, blah, 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 equals another differential, blah, blah, blah. I can integrate, et cetera, and the differential equation can be solved, all right? If it's a nice, easy to play with one like these are compared to others. So I can write dq dt as, I can pull out that RC, which I have to create one, I have to throw a C in there to make it work out. And so this will be Q minus CV. Now I extracted a negative, okay, so that I could turn V minus Q into Q minus V, but I had to throw a C in there. All right, so I'm not going to, this is algebra, all right, and you don't have to be able to do all that stuff. So now what we can do is bring the Q minus CV over to where dt is and bring dt over to the other side. And then we're in business for getting a solution to a differential equation. So Q minus CV will equal minus dt per RC. All right? That is something that can be integrated. But I'm out of room on this screen. So I'm going to get a new screen. So let's pick up with where we left off. We had dq per q minus cv equals a negative dt per rc. So if I integrate these two things, and so I'm going to integrate from 0 to q and 0 to t over here. All right? This is pretty basic stuff. So the natural log of q minus cv over minus cv will equal negative t over rc, which means q minus cv per minus cv will be e to the minus t over rc. Just basic undo the, or convert a natural log to its exponential form. And so what do we get out of this? Well, we can skip through some algebraic maneuvering. Charge will equal CV times 1 minus e to the negative t over RC. Well, CV is just total charge. That's the definition of capacitance. Lets me turn charge, capacitance times voltage into charge. And in fact, this will be the final charge. Okay? And it'll still have this 1 minus e to the minus t over RC. So this is a time-dependent equation. We can put t in here. All right. So I have a charge buildup equation. And it's the solution to a differential equation that comes out of applying Kirchhoff's laws to a resistive capacitive circuit. Now, the interesting thing about capacitor charging and discharging, and the same for inductors, is these functions of E, which are nice to play with because they integrate and differentiate nicely. You know, you get to keep getting the same thing out. What happens is you get a time constant out of this. What happens is as this curve is increasing or growth or decay, every time interval is 63 point something percent of the whole, or what's remaining. So you get 63% buildup or decay in the first time interval. Then you get 63% of what's left in the next time interval, and 63% of what's and so that keeps building up, 63, 80 something, 90 something, 90 more something, 99 something. So after 5, 6 time intervals, or what we call time constants, you've fully charged or discharged. But that'll be true for any exponential growth or decay function. Radioactive decay, all right? After 5 or 6 time constants, it's all decayed away. You're onto some other thing. So that's just a feature of that. And by the way, we should note that by time constant, we mean this little thing tau. This is more conventional. You'll see this in some physics textbooks. Forget whether ours does it or not. And if you're electrical engineer, you take an electronics course, you definitely will see tau, Greek letter tau, in place of RC, but we know that that's the time constant. So I can know in advance with a resistive capacitive circuit what the time constant's going to be. Some number of milliseconds usually. You know, so 500 milliseconds is half a second. How long does it... And so within a couple of seconds, you know that capacitor is going to fully charge or discharge. If it's 100 milliseconds, then it'll fully charge and discharge in less than a second. Those sorts of things you can know immediately. And so this would become, if you put tau in there, you would just have tau, T per tau. So it would be Q equals Q times 1 minus E to the minus T over tau. That's more conventional, the use of that time constant, or tau, which is just equal to the RC product. All right, little factoid. Not hugely important for physics, because that's a direct application to electronics. Hopefully it'll ring a bell someday. Oh yeah, I heard that once before. All right. So that's charging a capacitor. Yay. What about discharging? I'm glad you asked. So, applying Kirchhoff's laws again, so we're going to get minus, this is a voltage drop, so as the current drops out through the resistor, minus the voltage through the capacitor, okay, and that's going to be, that has to equal 0. Sorry. Those are the two voltage drops in the circuit. So you're going to get R dq dt will equal Q per C. All right. And that means dq per Q will equal dt per RC when you go to integrate from initial charge to final charge, 0 at a time. You'll get natural log Q per Q naught equals the negative T over RC. All right, so we'll get Q equals Q naught e to the minus T over tau. another equation. So here's the thing. One equation is a 1 minus e to the blah, 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 and the other equation is just a multiplier e to the blah, blah, blah. They have exactly the same structure, except one of them is a 1 minus, and the other one is not. Is a 1 times, if you will. All right? So that's a nice thing about the charging and discharging rules for discharging. So that's a simple one. I'm not going to labor that much more. Not at all. So what about RL circuits? Meaning, let's put a battery in here, a resistor, and a coil, otherwise known as an inductor. I need to throw a switch in here. So resistance, inductance. So you close the switch. We're going to get current flowing through here, but if you recall, we have an induced voltage opposite to the current flow, okay? That happens in that coil. That's taking us back a few pages in lecture, all right? So once again, Kirchhoff will have a thing or two to say. So the voltage minus the voltage drop through the resistor minus the voltage drop through the inductor. We just worked that one out a little bit ago when we defined inductance. So di dt will equal V minus IR per L, I think, yes. So V per L minus R per L times I. Now, some things to consider. Let's pay attention to something here. So di dt initially, okay, is going to be just voltage per inductance, okay, and what's happening here, you know, I is going to equal 0 at the instant that the switch is closed. At that very moment, you don't have you close the switch, you don't instantly have current. You don't instantly get anything in reality. Okay, it's always up the time. So there's this just, all we have initially is V per L at that very time equals 0 instant of the switch being closed. All right. The di dt final, okay, is going to be 0 after it builds up, and that's going to have to equal the V per L minus R per Li. Okay? Which just means V per L equals R per Li, which just means I equals V per R, which is just Ohm's law. So this little side exists largely to just kind of, I get back Ohm's law. That's good. All right, it shows we're on the right path. We'll still be able to use it. So nothing. So all right, so continuing on. So di dt is V minus R per L. That's going to take me to, if I rearrange stuff, now I skipped a few steps because it's algebra, all right? You want to work it out later? Work it out, okay? But I've set it up again so that I've taken the differential parts that were combined into a fraction and separated them so that I could integrate them, which means I had to convert some voltage and currents to their opposites or their counterparts according to Ohm's law. So we once again integrate this from 0 to I, this from 0 to t, and what we get is I will equal V over R 1 minus E to the minus R per L times time. Okay. Note that the time constant for an inductor or for an RL circuit is L per R. So we would end up flipping some things around in that exponent. I'm not going to bother with that because it's not hugely important. Okay? But the important thing here is that we solve differential equations. 2 for the charge and discharging of capacitors, and 1 for the behavior of an inductor. Okay? And
What's that E raised to?
the minus R per L times T. So R per L is a fraction. It would be minus RT per L if you wanted to resolve it as a fraction. Normally, though, it's going to be T over tau when tau is L over R, because they would want it to match up with the capacitor thing. Again, that's not important, okay, because this isn't an electronics course. Okay, what's important is the behavior. We applied Kirchhoff's laws to a device that obeys Faraday's law, or Kirchhoff's rules, which are conservation of energy, to a device that follows Faraday's law. That's the thing here. Calculus-based physics that leads you to what you would learn in, say, an advanced electronics course. Okay, so in fact we have, did anybody here take that electronics course last spring? Okay.
You got R over L in the exponent, but L over R in the cap.
Right. And so if you flip things around, you would have T per tau. I didn't put tau in the blue yet. There's a note. So there's a time constant for capacitors and inductors. It's RC for capacitors. It's L over R for inductors. And so the advantage there is that you can say, look, how long will it take to achieve it? You know, what's the time constant going to be? Or you pick one that has the time constant you want. Because you know after 5 or 6 time constants, you're fully whatever. Charge, discharge, built up, whatever it is. Okay? So